We are going to start the second lecture. So the plan for today is we have a first lecture, we have a small pause, and then we have a second lecture, and then tomorrow Pedro Salomão comes, he gives the final lecture, and that's the end of the mini course. So it's a pleasure for me to introduce again Urs Frauenfelder from Augsburg. He'll continue to talk to us about the three-body problem.
Thank you very much. So welcome everybody back. So let us recall what we discussed yesterday. So yesterday we introduced the planar circular restricted three-body problem. So we have a parameter mu in 0, 1, and we have two masses, which we call S and E. So S, the Sun, is at minus mu 0. The Earth is at 1 minus mu 0. And the Hamiltonian, H, this is on the cotangent bundle. From R2, we take out the collisions, Sun and Earth, to R. QP is mapped to 1/2 p square minus, so mu is the mass of the Earth, so we have gravitational potential of the Earth, Q minus E minus 1 minus mu Q minus S, which we can write alternatively as 1/2 P plus P1 Q2 minus P2 Q1. So this is because we are rotating, and we can write this alternatively as P1 plus Q2 square plus P2 minus Q1 square minus mu Q minus E minus 1 minus mu Q minus S minus 1/2 Q square. And these three terms we refer to as the effective potential. Now I would like to discuss two limit cases. And the first limit case is what happens when mu goes to 0. So what does this mean? Mu goes to 0. This means the Earth has no mass anymore. So the moon is just attracted by the Sun. So we have limit cases. So we have mu equals 0. So that there is, so Earth is massless. And so we have actually just a two-body problem, moon attracted by the Sun. But because of this term, we are always in rotating coordinates. So this is the so-called rotating Kepler problem. This is Kepler problem in rotating coordinates. So this is a rotating Kepler problem. i.e. Kepler problem in rotating coordinates. And so this Hamiltonian depends, of course, on mu. So if we have H0, so H0 of QP, this is just 1/2 p square minus, now we have just the potential of the Sun plus angular momentum, which we can also write 1/2 P1 plus Q2 square plus P2 minus Q1 square minus 1 over Q minus 1/2 Q square. So we still have Coriolis force and centrifugal force and just gravitational potential of the Sun. So this is our UQ. And now what you see, so what is special in the case mu equals 0, for mu equals 0, the whole problem becomes rotational invariant. This is not in this case, the problem is not rotational invariant. So we have here Sun and Earth, and we cannot rotate. But if the Earth vanishes and just the Sun is left, we can rotate. So this is rotational invariant. And U of Q just depends actually on the absolute value of Q. So let's call this R, where U of R is minus 1 over R minus 1/2 R square. And then if we look for the critical points of U, so this is now different from before. Before we had these 5 Lagrange points. So in this special case where everything is rotation invariant, also the critical points will be rotation invariant. So we just have to differentiate U prime of R. This is 1 over R square minus R. And if this is 0, then it follows that R is 1. And the critical value, U of 1, this is minus 3 over 2, if you plug this into this formula. So we have the rotating Kepler problem has just one critical value and a whole critical circle. So we have one critical value and a circle of critical points. And the Hills region so we have Kc, which is, so we have projection of the energy hypersurface. So sigma c is H inverse of C, and P is from T star R2 to R2. The foot point projection. Then if C is less than this critical value, we have two components of the Hills region. So the moon is, so everything is rotationally invariant. So the moon is either close to the sun or is a comet far away. And if C is bigger, 3 over 2, then Hills region is everything, so you can be everywhere. So Kc is just R2 origin. So the rotating Kepler problem is already in the work of Poincaré plays quite some role, because if you want to find periodic orbits in the restricted three-body problem for small mu, then you first look at periodic orbits in the limit case, in the rotating Kepler problem, for mu equals 0. And then you look at the family. So then you start switching on the Earth and look at the family which occurs. And what are the periodic orbits in the rotating Kepler problem? So this is always a bit confusing, because if we start rotating our coordinates, so what were periodic orbits before, don't need to be periodic orbits afterwards if our coordinate system is rotating. So in the Kepler problem, for negative energy, basically every orbit is periodic, the ellipses, except the collisions, but we can regularize them, and then they are also periodic. Where in the rotating Kepler problem, the orbits are, you have ellipses, but now the system is rotating, so the ellipse makes something like this. And it might close up or might not close up. It precisely closes up if the period of the ellipse is a rational multiple of 1. So orbits in rotating Kepler problem they are rotating ellipses. So you have an ellipse. That's ellipse. This is in the Kepler problem. Kepler ellipse. And now the picture you get is quite amazing what you can get. So you can play a bit with computer because you need to plug in the parametrization of the ellipse, which is not completely trivial. You know by Kepler's law, same time, same area. So the parametrization is here you're a bit slow, here you're fast, slow, and so on. But now you start rotating this whole thing, and you will get amazing pictures if you do this. So you will get something like you do like this, and then something like this. So beautiful curves you get. So this is a rotating ellipse. So this is periodic. This is not necessarily periodic. And it's periodic. There are two ways to be periodic. So one way is if the Kepler ellipse is a circle. So if you rotate the circle, then it's still the circle is mapped to itself. So it's periodic if ellipse is a circle, or it's periodic if the period of the ellipse is a rational multiple. If it's rational, if a period of ellipse is rational. And if you look at the families you get in the restricted three-body problem, so this goes back to terminology of Poincaré. The orbits you get from the circles, these are called periodic orbits of the first kind, and these are called periodic orbits of the second kind. So the families for mu bigger 0, these are periodic orbits of first kind. They are rather close to circles, and these are periodic orbits of second kind. And they can look quite crazy. Huh? So, and this goes somehow back to Poincaré, but this was also then studied by Arenstorff, and sometimes they also refer to as Arenstorf orbits. And they were also 50 years ago when people tried to go to the moon, they also played a role there as the Arenstorf orbits. So this is one limit case. Now, another limit case is, one would like to let go mu to 1. So, but if mu goes to 1, if you do it naively, then you just get again the rotating Kepler problem. And the only difference is that now you have here the Earth instead of the Sun. But everything is symmetric with changing Earth and Sun. But you can do it differently. And this is kind of a miracle that this works. This is the so-called Hill's lunar problem. Hill's lunar problem. Also, it's something like mu goes to 1, but we have to take this a bit in parentheses. So we have now extremely heavy Sun, which is infinitely much heavier than the Earth, but the Earth is still infinitely much heavier than the Moon. So we cannot compare anything anymore. So everything is on different scales. So we have the mass of Sun. This is much, much bigger than the mass of the Earth, and this is much, much bigger than the mass of the Moon. But what we want to consider is, and this fits with our Moon. The Moon is actually close to the Earth. So M is close to E. So we have this kind of picture. We have a very big Sun. We have an Earth, which is nothing compared to the Sun, but is still much, much heavier than this little point you barely see. This is the Moon. So here is the Moon. But the Moon is very close to the Earth. And then what we do is, we look here. We look here with a magnifying glass. So first, we change our coordinates. So we make the center of our coordinate system the Earth. Also make E origin of coordinates. That's harmless. That's just a translation. That is symplectic, and then blow up coordinates around E. And what we do is we have here the old QP goes to mu 1 over 3Q, mu 1 over 3P. So this blowing up the coordinate, this is not symplectic. So it is only conformally symplectic. So it's conformally with respect to a factor mu to the 2/3. And then, so we also scale our Hamiltonian. So what we want to change is our dynamics. So the dynamics is determined by the Hamiltonian vector field. So the Hamiltonian vector fields, we don't want that it changes, but we can scale simultaneously the Hamiltonian and the symplectic form. So we also scale the Hamiltonian. So we take the old Hamiltonian, and then this is kind of a funny thing. So we this 3/2 appears here again, and this 3/2, this is something we have seen before. This is precisely the critical value of Kepler problem. This is it's kind of nice that we have this critical value of the Kepler problem, and then we scale by 1 divided by mu2/3. So this, of course, adding a constant to the Hamiltonian does not change anything of the Hamiltonian vector field, but because we want to let go mu to 0, this is important because this will also explode. So we somehow renormalize our Hamiltonian. And then if we want to go back to the old Hamiltonian, so this Hamiltonian is basically the critical energy of the critical value of the Kepler problem, this -3/2, plus this new energy multiplied by mu to the power 2/3. So this has a new interpretation, this energy. It's not the old energy, something new. And so note, xh, this is invariant under this 2 scaling. And then the interesting thing is that the limit exists. So this is kind of an interesting point. Limit mu to 0 exists. And the limit Hamiltonian, how does the limit Hamiltonian look like? The limit Hamiltonian so if you can compute this by yourself. Well, if you compute it by yourself, you basically do Taylor. You develop everything by Taylor in powers of mu to the 1/3, and then let mu go to 0. But if you do this Taylor expansion, you will see that there's some magical cancellation of terms. And what you will get in the limit Hamiltonian is h. So we blow up the coordinates here. So the origin is now at the Earth, but the sun goes to infinity. So the limit Hamiltonian is defined on T star R2 without origin, and the origin is now the Earth, to R. And it maps QP is mapped to 1/2. So we still have this P1 plus Q2 square plus P2 minus Q1 square. We have still the Coriolis force. Then we have 1 divided by Q. This is the gravitational force of the Earth. This is not surprising so far. And then we get an additional term, -3/2 Q1 square. This last, so we have here a Coriolis force. We have here gravitational force of Earth. And this force I like to refer as kind of tidal force. So what does this additional force do? this additional force, if here is the Earth, then you have here the force is repulsing, and repulses just in Q1 direction, and it becomes bigger and bigger. It grows linearly. If you move away, that's like tide. So you will here, if you have here an ocean, then it will move in this direction, and here an ocean will move in this direction. And how does the tidal force appear physically? The tidal force is a combination of the gravitational force of the sun, which is now infinitely heavy, and the centrifugal force. So these two forces, they almost kill each other. They are very heavy, and so a tidal force, this is a combination of gravitational force of sun and centrifugal force. And let's make a picture to see how this So we have now this extremely heavy sun, but this sun is extremely far away. And we have here is our Earth, here is our Moon. So the center of gravity will be somewhere here, basically in the sun. So we have a huge gravitational force of the sun. But we also have a huge centrifugal force, because now we are very far away from the sun, so we will experience a heavy centrifugal force. And they basically kill each other, and the only left over is this term. But one should not. One thinks this is like a baby, this tidal force, but it's actually not completely harmless. If it would not be there, the whole system would be much more easy. Then it would be rotation invariant. So for example, this tidal force makes the whole system not rotational invariant. And already in this limit case, in this Hill's lunar problem, there is still a chaotic behavior. So it's not integrable, and at least there's no analytic integral, and dynamics is quite chaotic due to this baby here. But then there is another interesting point when going to this limit, that is we gain, and we are not rotation invariant, but still we have more symmetries in the Hill's lunar problem than in the restricted three-body problem. So let us discuss a bit the symmetries. So in restricted three-body problem, we have the following antisymplectic involution, rho 1, from T star R2 to T star R2, Q1, Q2, P1, P2. So what we do is we do reflection at the x-axis at Q1. So this we can do because this Sun and Earth, they both lie on the x-axis. So the whole system is invariant under this reflection. So we have Q1 minus Q2, but then because we also have the Coriolis force, we have to make the Hamiltonian invariant, we have to put here minus P1, P2. So you see that this term here gets two minus signs, and the square, and it vanishes again. So under this antisymplectic involution, the restricted three-body problem is invariant. So this is antisymplectic. So we have ρ1 square is the identity, and if we pull back omega, we get minus omega. But in Hill's lunar problem, we have an additional antisymplectic involution. So we have ρ2 T star R2 to T star R2. Now we also have rotational invariance under reflection at the y-axis. So this is not true. This is not true for the restricted three-body problem, but we have this invariance in Hill's lunar problem. Namely, we have here minus Q1, Q2, P1 minus P2. Which is kind of an amazing thing, because we don't have this in the restricted three-body problem. So you see how we got to this Hill's lunar problem was definitely not invariant under reflection at the Q2 axis, because we moved the sun in one direction. But we could have done the same thing. We could have flipped the sun here and move it here to infinity. And in the limit, we would have, both cases would get the same thing. So these two forces, they cancel basically each other, and so what remains is invariant on the reflection at the y-axis. So this is only Hill's lunar problem is invariant under ρ2. So what happens if we, what can we do with this antisymplectic involution? Because we have this ρ1, this leads to the so-called symmetric periodic orbits. So symmetric namely, suppose we are in the restricted three-body problem, and we have, as here we have the sun and the Earth, and we have an orbit. We start here perpendicularly, and we end perpendicularly. Then what we can do, we can use the reflection. We can use the reflection at the x-axis and flip, and we get the periodic orbit like this. That's a symmetric periodic orbit, and this observation is actually quite crucial in finding these periodic orbits. Or in this work by Arenstorff, this was used heavily. Already Poincaré knew about this and used it, and also Arenstorff when he found these Arenstorff periodic orbits, because there is always in the rotating Kepler problem, the circles, the one of the first kind, they are isolated. But the rotating ellipses, they come in whole circle families. Because you have this rotating ellipse, but then you can still rotate it. You can rotate the rotating ellipse, so you get the one parameter family of periodic orbits, so it's degenerate. So you cannot apply implicit function theorem directly. But if you just, inside this circle family, there are two symmetric representatives. And these symmetric representatives, they are isolated. And you can apply implicit function theorem to the symmetric ones. And that's the trick, so it's how you can get proof existence of these periodic orbits of the second kind for small mu by applying the implicit function theorem not to the periodic orbits, but to the symmetric ones, which are isolated. So this plays a big role in the restricted three-body problem, but now in the Hills lunar problem, you have two involutions. So in Hills lunar problem, we have, so here is now the Earth, the Sun is gone, it's far away, and if we start here perpendicularly at the x-axis, and we end at the y-axis perpendicularly, then we can use both reflections. So we first do reflection at the y-axis, so we continue like this. So then we have we are in this situation, and then we reflect this whole thing at the x-axis. So we have kind of doubly symmetric periodic orbits. So we have doubly symmetric. So now, of course, we would like to know what are there periodic orbits in Hills lunar problem. And so what can we do? What do you think? Are there periodic orbits or not? Yeah, let's look at the sky. And what do we see on the sky? We see the moon. And the moon comes every month. So moon is rather periodic. It's not completely periodic, but almost periodic. So I would like to that was Hill's idea, to describe the moon. The moon should be very close to periodic orbit. Let's try to find this periodic orbit, which is a good approximation to the moon. And now let's ask the astronomers, what kind of moons do you know? And then they know two kinds of moons: direct ones and retrograde ones. And what are these? Direct and retrograde moons. So we have the sun here. And the sun rotates. So this rotates. And then we have just 8 planets, so it's a bit hard to say we make a good statistics with 8 planets, but at least what all planets agree, they move. We have a planet here, it also moves the same direction. So that's, I think maybe a long time ago that was kind of eddy, so where this masses get concentrated, so everything was rotating like this. So in the middle, the sun is rotating and the planets they also rotate in this direction. That's and then the planets also rotate. And now this is only generic planet. Well, generic means 6 of 8. So most of the 6 planets out of 8, they rotate in the same direction. So generic planet. So 6 of 8 examples. They rotate itself in this direction. So the exception is Venus. This is Venus. So on Venus, the sun rises in the west and sets in the east. And then Uranus is quite exceptional because Uranus is also basically, when it has to go to R3, is very much inclined. So Uranus also does not fit good. And then the moon, so what are the generic moon doing? The generic moon does like the planet. So generic moon. So we have here the sun, we have here the planet, and the moon also like this. Here is the moon, goes like this. Everything in the same direction, and it's more or less periodic. So this is almost so kind of periodic orbit, and this is called the direct case. There are some exceptions. So probably the most interesting exception is Triton, the moon of Neptune. So Triton is moving other way around. And so, but for example, our moon does like this. No. No, maybe now we have exoplanets. Probably we also have exomoons, and maybe then one can say more. But this now I talk just about our solar system, and this is of course you can imagine a bit what's going on, but there's no mathematical statement. Now, so exceptions. This sun like this. Then we have here planet going like this, and the moon goes opposite. That's retrograde. And so example is Triton. It's a moon of Neptune. There are others. Jupiter also has some, but these are usually rather little, tiny moons, where Triton is rather big. Good. So for astronomers, and this since the time of Hill, since this is an old problem to how do we describe the orbit of our moon? So we would like to have a periodic orbit, a direct one. Now, mathematics is a bit funny. So I actually don't know a real analytic proof of existence of this direct orbit even in Hill's lunar problem for all, let's say for all energies below the critical value. Numerically you can find them very well. But the funny thing is, there is an analytic proof about existence of the retrograde orbit. So the one which is not so important in astronomy, for mathematical purposes, it becomes very important because we can prove that it exists. And this proof, this is Birkhoff, and Birkhoff give analytic proof of the existence of these retrograde orbits for Hill's lunar problem and for restricted three-body problem below the first critical energy. And this proof I would like to discuss a bit.
Does this have to do with the tidal force? Like, is that what makes you have a retrograde moon? Or?
Here is more the Coriolis force is more important. The Coriolis force here is crucial. But the tidal force just makes the problem complicated. But the Coriolis force gives, because without Coriolis force, everything would be, if you have an orbit, you could just go backward. Without Coriolis force, if you have a retrograde one, we can just go backward the retrograde if a direct one. But because of Coriolis force, we cannot do this. So going backward is it doesn't give you a periodic orbit in general. Birkhoff's analytic proof of existence of retrograde below first critical value. As a proof works also for a restricted three-body problem, but I would like to explain it for Hill's lunar problem. For Hill's lunar problem, because there we have this additional symmetry which makes the proof easier. We just have to shoot 1/4 and not 1/2. Maybe let's add some more information about this Hill's lunar problem. So what are critical points and critical values in Hill's lunar problem? So that's a question for you. So can you figure out how many critical points should be in the Hill's lunar problem? How many do you expect? Recall we had 5. Had 5 in the restricted three-body problem. Do you also expect 5? No. Good, good. So how many do you expect? Not 5. Yeah, that's correct. So we have critical points in Hill's lunar problem. So recall we had the 5 Lagrange points. Four. Even less. Let's once more draw the case of the restricted three-body problem. The restricted three-body problem, we had Sun and Earth, but now the Earth, we should think this is kind of tiny. And now we have Lagrange points, and maybe because this is tiny, this L1 is quite close to the Earth. Here is L1. Then here we have also L2 on the other side of the Earth, but also quite close. Then we have L4 and L5, so they are quite far away. And then we have L3 on the other side of the Sun. And what do we do? So you recall we look in this region with the magnifying glass. So we will see the two. Here we do the magnifying. So we will actually see two critical points. There are two critical points. And as you can, as an exercise, you can also compute them. So this kind of, if you like number theory, I'm not sure, so it's a kind of funny number, plus minus 3 to the minus 1/3. What we see here is they are now symmetric with respect to the y-axis. And this has to be, because we have this additional symmetry. So before in the restricted three-body problem, L1 and L2 were not yet symmetric. But now in the limit they become symmetric. So they are symmetric with respect to the y-axis. And because they are symmetric with respect to the y-axis, then we also have just one critical value. So we have one critical value. And this critical value is minus 3, 4/3, 2. But you have to remember that the energy here, the energy in the Hills lunar problem, there is not such an easy connection between energy in Hills lunar problem and the energy of the restricted three-body problem, because we did this renormalization. So that means if you go back to the restricted three-body problem, the energy in the restricted three-body problem is this minus 3/2, the critical energy of the rotating Kepler problem, minus this value to the power μ2/3. And then the Hills region, so if C is less than minus 3, um, 4⁵/2, so it looks it looks like this. So it's so here we have these two L1 and L2, and we have here is our Hills region, and then we have also we have two unbounded components. This, which are leftovers from, as we had here, leftovers from the Hills region around the Sun. This is the one on the left, and the unbound in the restricted three-body problem, the one on the right. So that is the Hills region. And so let's suppose we are this situation. So suppose C is less than minus 4.3 over 2. And now what is Birkhoff's shooting argument? So what is the idea? So what do we want to find? We want to find, we shoot here from the x-axis perpendicularly. Here we shoot to above. If we would shoot down, this would give the direct, but there are some problems in the proof. So we shoot in this direction to get the retrograde. And so we shoot here, and then probably we are unlucky. So we will end up here with some angle, which is probably not 90 degrees. So then we shoot everywhere. And we just try everywhere until we find some nice shot where we hit perpendicularly. And if you go here further, it might be like this. So the problem is we have to make sure that we will be successful, that there is a point like this where we shoot perpendicularly and also will end here perpendicularly. This is a priori not clear. Why should we find such a point here? Now what we do is we first shoot very close to the Earth. If our moon is very close to the Earth, so here, then we have basically a Kepler problem, and we know what happens in the Kepler problem. So we can if we shoot here, we can precisely say what the orbit is. So idea, first start shooting very close to E. Then to E. So that's roughly a Kepler problem. And then what happens is, so if we shoot here very close, we will have some kind of Kepler ellipse. And what we will see here, we have an angle which is too less. It's not 90 degrees. It's something like, I think if you compute it's something like 45 degrees. So here we have, here our angle is less than pi over 2. Now we move. Move to the left. And then what Birkhoff's proof makes so interesting is that his proof proves more. So he proves existence of the retrograde, but he gives us additional present. So he gives us an additional interesting orbit, namely a symmetric collision orbit, which is a byproduct of his proof. And that's probably the reason why this proof does not work for the direct one, because he gives us this additional present, and this additional present we don't have in the direct case. So it's not clear how to generalize this to the direct case. So proof is too nice, so it gives us too much. We should have a more modest proof, but we don't know if such exists. So find, and this is kind of miracle. So this I have to explain why we can do this. So find a consecutive collision. So maybe a symmetric consecutive. So namely, if we move, then there will be a point when we shoot here, we will like this. And this, why is this a symmetric consecutive collision? You could, everything is invariant on the reflection at the y-axis, you could reflect this to get a consecutive collision orbits, which is symmetric. So this is the present Birkhoff gives us in his proof.
Isn't the point that we can't shoot down because it's not actually symmetric? Because when we change Q2, we need
What you can, this here, we cannot just change if you have this, we can just change the direction. Also, if we, here we will come from this.
Oh, you come with the same.
Yeah, right. So you can, so we have this anti-symplectic involution where we reflect, but also have to go backward. We have to do both simultaneously, reflect and going backward. We cannot not just going backward is not enough. That's not the symmetry because of the Coriolis force. So this is this is the goal. And then if you have this, then you just before we have this consecutive collision. Here again, we are very close to the Earth, so we have basically a Kepler problem. So here we can see what happens. And then just before this consecutive collision, before collision, so we have, so here we have the collision, and then here just before, we will have almost a collision, something like this. But here you see the angle here is more than pi. Here the angle is bigger pi. And now we use the intermediate value theorem. So we have, so if you shoot very close to the Earth, we have angle less than pi, then we move. The angle changes, and at one point it will be more than pi, pi over 2. So it is more than pi over 2. So somewhere the angle has to be pi over 2, because continuity. So then here, so we have here is angle less than pi over 2. Then we we shoot, then somewhere here we have this consecutive collision, and somewhere in between we have to have angle pi. Here is pi. Here is bigger pi over 2, and here is less than pi over 2, and intermediate value theorem. Here we have pi over 2. Okay, that's the idea. So how do we guarantee this? So how does Birkhoff proof work? So I'd like to sketch his proof. So the first thing is, in the first step, you really have to use a bit the special physics. You have to write down the equations of motions, and then with the equation of motion, you do kind of elementary estimate to show that wherever we shoot here on the x-axis, the orbit will, after some time, it either will hit the x-axis or the y-axis. But what cannot happen is that the orbit stays forever in this quadrant here. It has, at some point, it will go out of this first quadrant. So step 1 is use equations of motions and then you show wherever you shoot, either this or you will hit the y-axis, or this, but not, for example, this is not possible, that you shoot here and this doesn't happen, that you stay here for forever in this first quadrant. Doesn't happen. And actually, so if you look at the estimate, what you actually see is when you cross here the x-axis, you will actually cross it with you have some positive velocity in this direction, or also here you have some positive velocity. So what also doesn't happen is just that you just touch this x-axis. So this is step 1 where we use the equations of motion. Then step 2 is now we know that it might happen that we hit the x-axis first before we hit the y-axis. But what Birkhoff then rules out is it's fine to, if you have this general picture, it's fine to hit the x-axis at some point, namely after these consecutive collision orbits. But what we don't want is that we hit it already before. So if we start moving here and move back, we want that we first always hit the x-axis, the y-axis, until we have this consecutive collision, and after that we hit the x-axis, not already before. So step 2 rule out this. So namely that we just touch We don't touch the x-axis. And this we can actually understand why we can rule this out, since this is because of course, why does this not happen? If this would happen, we would have here at this point, we have gravitational force. Here we have gravitational force. And we have here our tidal force. Tidal force is repulsing. But then here we're moving in this direction. So we would also have Coriolis force in this direction, which contradicts because we are moving upward again. So we have here Coriolis force. This is a contradiction. So this doesn't happen. So that is the only way, if we once go through the x-axis, we have to go first to the collision. So we have now two possibilities. Either we will always go to the y-axis, or we also go to the x-axis, but we have to go through this consecutive collision. So consequence. So either we have always until we are at the end of our Hills region, we always will hit the y-axis, or this scenario, we go like this, then somewhere we will have this consecutive collision, and then we can go through the x-axis, 1 or 2. And then the last step is this occurs and not this. Step 3, scenario 2. 2 occurs. And then what you do to show scenario 2, you go to the extreme point, namely you go to the boundary of the Hills region. Boundary of the Hills region has a following physical interpretation. The boundary of the Hills region, these are the zero velocity curves. So you have no velocity. You have acceleration, but no velocity. So go to boundary of Hills region. So here is our Hills region. And now we are here. We start here, this point. This is the zero velocity curves. Now, what happens if we start here, this point? So you will be accelerated toward. So the Earth is attracting you. It's strong because it's stronger than the. You can go outside. So it's stronger than the tidal force. So you will have first some force in this direction. So the orbit starts moving in this direction, but as soon as he moves in this direction, if he has some velocity, he will also feel Coriolis force, and the Coriolis force brings him down. So he goes first a bit in this direction, and then he feels, here is Coriolis force. So he goes down. Now, what happens just before you came to this orbit? Yeah, the flow is continuous. So here you will go a little bit up, but then you also have to go down because you're close to this orbit, which goes down. So that means just close before the zero velocity curves, your orbit will actually have to hit the x-axis. And so we are in scenario 2. So we have the orbit here go down. And then if you look at an orbit close by, here we shoot a little bit, but we have very, very few velocity. We were very close to the zero velocity curve. So we have a little velocity going up, but then goes like this. And so we hit the x-axis. So so we are in scenario 2. And that's the idea behind the proof. Okay, so we have now our retrograde orbit. But here we really used retrograde motion. We need this Coriolis force, which we cannot just flip sides. So this proof doesn't work for the direct one. So question is, can we give an analytic proof of the direct one? Or does the moon exist? So do we have this periodic orbit? And then Birkhoff had a very interesting idea, and this goes, Umberto will explain more about this idea. So Birkhoff's idea, so he made a conjecture. You could now conjecture the direct exists. But this conjecture is much more interesting. His conjecture is that this retrograde orbit, after all this regularization we explained yesterday, after this Levi-Civita regularization, bounds a disk-like global surface of section. Birkhoff's conjecture. And everything below the first critical value, first critical value, after Levi-Civita regularization, retrograde orbit bounds global surface of section. So Umberto will talk much more about this topic. So let me just mention briefly what this is about, and Umberto will then discuss this in detail. So what is our, so we are on this energy hypersurface, which is of the regularization is an S3. That's like our room here. So it's three-dimensional energy hypersurface. So this is, we have some flow here. So on each point we have some vector. And we want to follow this vector field, compute the flow, which is rather tough. Now, what the global surface of section does is it discretizes the problem. So a global surface of section, this is just a disk, like here. So we have this dynamical system in 3 dimensions. In each point we have a vector. But now here we have somewhere in this 3-dimensional space we find an embedded disk. And the boundary of this disk, in this case will be the retrograde orbit. So the boundary, so the Hamiltonian vector field is transverse to the boundary, but in the interior will be opposite. It will be, it's tangent at the boundary, but in the interior it will be transverse. So we go out, but then the global thing, the global property of this global surface, that's what makes it global, is we will come back. So we go here. Here we start with a point here. We go somewhere in this room, but after maybe we go behind this blackbird, but after some time we will go back, come back. And this is for every point. And also if we start with an arbitrary point in this room, in forward and backward time, we will come back to this global surface of section. So this global surface of section basically, this stores all information. It discretizes our flow, but all information about our flow is contained in this global surface of section. And then so what we have here, so we start with a point and we go to the next return point. So we have x here, and so this is Poincaré return map. And everything is symplectic. So in symplectic geometry, there's no friction. So that means this Poincaré return map is area preserving. So psi is area preserving. And now shortly before Birkhoff formulated his conjecture, Brouwer proved that an area preserving disk map has a fixed point. Brouwer area preserving map of disk has fixed point. So here we have our disk. So we have here some fixed point. And if you have a fixed point of this Poincaré return map, so the orbit, this is then a periodic orbit. And that would be the direct one. So that's how Birkhoff wants to find the moon. And Umberto will continue with this story. Thank you.